Hello everyone. In this import video we will see a very important concept of real analysis, which is sequence. So what is a sequence? A sequence is a function from the set of natural numbers to any set S. Okay, we are all familiar with this term function, the natural numbers, and the term set, right? So let's see what is a sequence by considering examples. So my first example will be, let's call the function a(n) to be a of n, and it is my n only, the identity function, right? This is the way to denote a function, basically as the nth term of a function. The a operating on n, I can denote it by an. Okay, so what will be my range set? The range set will be a of 1 will be 1, right? So therefore my first element will be 1, a of 2 will be 2, a of 3 will be 3, and so on, right? So this is my range set, and this is called my sequence. The second example can be my an equal to minus 1 over n, right? So what will be my range set? My range set will be 1, minus 1, 1, minus 1, and so on, right? What can be my third example? Let an be 1 over n. Okay, so what will be my range set? It will be 1, 1 by 2, 1 by 3, 1 by 4, and so on, right? So what we have seen three examples, three very trivial examples of a sequence. So what is a sequence? A sequence is a function from a set of natural numbers to any set S. So what is my function here? In the first example, my function is a. Okay, a is from the set of natural numbers to a set S. In my case, S is also natural numbers, right? In second case, in the first example, my a was a of n is n, right? In the second example also, my a was from the set of natural numbers to natural numbers, right? No, not to the set of natural numbers, it is to the set of integers. Basically it was minus 1 comma 1, right? And my a n was minus 1 to the power m. In my third example, my a was from the set of natural numbers to the set of a set S, where S is also from 1 over n, right? And an was my 1 over n. So basically what we have seen that S can take any form. In the first example it was my natural numbers, in the second example it was a subset of integers, and in the third example it is a subset of real numbers of the form 1 over n, where n is any natural numbers. Okay, now we will see what is meant by limit of a sequence. Okay, so we are all familiar with this term limit, and we have calculated limit of a function very trivially, very easily. We can find limit of any function, right, if it exists. So in the same way, since sequence is also a function, so in the same way as we find the limit of any function, we can find the limit of a sequence. For example, I can find limit n tend to infinity of my an, where an is n. Okay, so this is limit n tending to infinity of n, which is infinity, right? It is very clear. We can prove it also. We are all very familiar with this terminology, right? So this was my first example. My second example was n tend to infinity an, where an was minus 1 over n. Friends, I will leave this example for the future reference. I will not explain what will be the limit of this sequence. I will come back afterwards. Okay, what was my third example? Third example was n tending to infinity an, where an was 1 over n. So we all know that limit n tend to infinity 1 over n is 0. So therefore limit n tend to infinity of an will be 0. Now, having talked about the limit of a sequence, we can talk about its convergence as well. So what is meant by convergence of a sequence? A sequence an is said to converge to a real number L if for every epsilon greater than 0 there exists a natural number n0 such that mod of an minus L is less than epsilon whenever n is greater than n0. Okay, so this is the formal definition of the convergence of a sequence. I can show you to explain what is actually meant by convergence by an example. Suppose my example was an equal to 1 over n, right? So let me draw a graph of this function to the correspondingly scale. You can scale it according to yourself. Okay, so this is my an and this is my n. Okay, so let this be 1 and this is my 1 also. Fine. For 2, let it be 1 over 2. The scaling is up to you. Okay, so let accordingly, therefore 1 over 3, 1 over 4 and so on, right? So finally it will converge to 0 at n tend to infinity, right? So therefore, by the definition of the convergence, my L is 0, right? So what it says, the definition says that if for every epsilon greater than 0 there exists a number n0, right? So let epsilon be here something. This is my epsilon. So this is this whole line, the length of this line is epsilon. So therefore for every epsilon there exists an n0, right? So let's draw an horizontal line with the parallel line with respect to the x-axis, the n-axis basically. So this will be my n0, right? You can choose n0 to be this. So after this n0, right, my an minus 0 is less than epsilon, right? This distance is less than this distance, right? This distance is my epsilon and this distance is my an minus, this distance is my an minus 0, right? So this is my n0 plus 1, n0 plus 2, this is my n0 plus 2, this is my n0 plus 3 and so on, right? So after this n0, my an minus 0 will be less than epsilon, right? So therefore for this epsilon my n0 is this. For a smaller epsilon you can choose the n0 in the same way. You can draw a parallel line with respect to the n-axis and have an epsilon and have a n0 corresponding to that particular epsilon. Okay, if I choose my epsilon to be 1, then my n0 will be 1, right? It will be my 1. If I choose my epsilon to be 1 by 2, my n0 will be 2, right? So therefore for every epsilon greater than 0 you can choose an n0 in the same way as I have chosen in this particular case. Okay, so we have seen what is meant by convergence graphically and what is the formal definition of the convergence. Now, like limits of a function, limit of a sequence is also unique. Okay, so what's the proof of this thing? So let on contrary an converges to L1 and an converges to L2 simultaneously. Okay, so by the definition of the convergence, for every epsilon greater than 0 there exists n1 in natural numbers such that mod of an minus L1 is less than epsilon by 2 for all n greater than or equal to n1, right? Similarly, For every epsilon greater than 2 there exists n2 greater than, belonging to the natural numbers, such that for every epsilon greater than 0 there exists n2 in natural numbers such that mod of an minus L2 is also less than epsilon by 2 for all n greater than or equal to n2. Okay, so let my n naught be maximum of n1 and n2. Okay, so therefore for every epsilon greater than 0, an minus L1 will be less than epsilon by 2 and an minus L2 will also be less than epsilon by 2 for all n greater than or equal to n naught, right? You can see this very easily. We have seen this in the case of limit of a function, right? So therefore an minus L1 and an minus L2 will be simultaneously less than epsilon by 2. So let's consider L1 minus L2 mod. Okay, so this will be equal to L1 minus an plus an minus L2, right? So by triangle inequality this will be less than or equal to L1 minus an plus an minus L2, right, for all n greater than or equal to n naught, and this is less than, strictly less than epsilon by 2 plus epsilon by 2, which is epsilon, and this is true for every epsilon greater than 0. Therefore L1 minus L2 mod is equal to 0. This implies that L1 is equal to L2, right? So therefore we can say, we have seen that limit of a sequence is unique. Okay, now since there is a concept of convergence, so there must exist a concept of divergence, right? So what is divergence? See, we say that limit n tend to infinity an is L, then we say that an converges to L, right? An converges to L, right, where L is any natural real number and L is not equal to minus infinity or infinity, right? Now what if limit n tend to infinity an is plus minus infinity, plus infinity or minus infinity at a time? So what if this happens? We say in this case that an diverges, right? DGS is my short form of diverges, and divergence I write DGENS. Okay, DGENS means divergence. So when limit an is equal to plus or minus infinity, then we say that an diverges. If limit an tends to infinity, an is plus infinity, we say that an diverges to plus infinity, and if it is minus infinity, then we say that an diverges to minus infinity. Many authors categorize a sequence as convergent and divergent, right? But I categorize this any sequence into three categories, that either convergent or divergent or oscillatory. Okay, so what is convergent sequence? We have seen an example of divergent sequence. I can give you limit n tend to infinity, n is infinity, right? So therefore an equal to n is a divergent sequence. Okay, similarly limit n tend to infinity, n over log L. Okay, so its graph is like this, and y equal to x graph is like this, and y equal to log s is, the graph is like this. So limit n tend to infinity, n over log n will be infinity, right? We can check it also by L'Hopital rule. So therefore an equal to n over log n is a divergent sequence. Okay, So I categorize a sequence into a third category, which is oscillatory sequence. So I want to remind an example I gave you earlier, which was an equals to -1 to the power n, where n is any natural number, right? So what will be the value of an for n equal to 1? It will be -1. For n equal to 2, it will be 1. For 3, it will be -1 again, and so on, +1 and -1, right? So in general, I can write the formula as a of 2n as 1 and a of 2n minus 1 as -1. So every even place I get 1, and every odd place I got -1. So basically, what type of graph I will get? I will get like -1, then +1, then -1, then +1. So basically we can see that there's an oscillation about the x-axis, right? This is called oscillation. You must be knowing this concept. So this kind of sequences I categorize into oscillatory sequence. Okay, many authors categorize this kind of sequence into divergent sequence, but I don't think that divergence is the right word for this kind of sequence, because it doesn't diverge to any plus or minus infinity. It basically oscillates. So I categorize sequences in convergent, divergent, or oscillatory. Okay.